Algebra 2 Honors 4.6a notes. So we are going to be looking at the fundamental theorem of algebra today, and we are going to be using that along with complex conjugate pairs for polynomial functions and Descartes' rule of signs, which actually will be day 2. And so the directions. You must show use of rational root theorem by listing all possible rational roots and doing synthetic division to find at least one or more real zeros and factor the remaining quadratic or use the quadratic formula as necessary. Use the process outlined in the notes. You can use decimals to help narrow the choices, but all that work for the synthetic division and listing possible rational roots needs to be there. So the fundamental theorem of algebra: if f of x is a polynomial of degree n where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. Corollary: if f of x is a polynomial of degree n where n is greater than 0, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solution or 3 times is counted as 3, etc., etc. Just so, corollary, in example 1 here, how many solutions does the equation x to the fourth minus 2x cubed plus 5x plus 12 equaling 0 have? Your answer to that is 4. Provided, of course, we're counting each repeated solution for the number of times it's repeated. But so the answer to that needs to be 4. How many zeros does this function in part B have? Well, the degree of it is 3, so it has 3. And so that's part of the fundamental theorem of algebra. And so they give you some examples here that this first one is linear. It's 2x to the first, so it has one solution. X squared has 2 solutions. X cubed has 3. X cubed, both the last two have 3 solutions. And they're listing them. And that's what we're going to be working on, or finding the solutions to those equaling 0, starting with using the rational root theorem as needed. So finding the zeros of a polynomial function, find the rational roots. Factor at the beginning if possible. If not, use the rational root theorem. Remember, some values might produce repeated solutions, and you may need to try that number more than once to reduce the polynomial sufficiently. Then once you get it down to a degree 2, you can factor or use the quadratic if needed. Write f of x in factored form. You need that in your work, and find the complex zeros where applicable. So we're going to find the zeros in example 2 of this polynomial. And so I want to see rational roots. It's to the 5th degree. We don't even know how to do that by grouping. So you need to show the rational root theorem. Yes, there might be programs out there that would help you with some of that, but you need to list. We're going to just do P over Q like this. And we're just going to make a long fraction. For 36, it's 1 times 36, 2 times 18, 3 times 12, 4 times 9, and 6 times 6. So there's quite a list there. And all over factors of 1. So overall, your list is just going to be those factors of 36. And so you need to have that list. That's required. And now we want to try to reduce this to get it down to quadratic. So that means I need to find 3 roots or zeros or solutions so that I can get it down to something quadratic that I can factor further or use the quadratic formula on. And so I'm going to start with 1. And if I use 1, I've got a 1, 3, 9, so 5, 4, 3, 23. There is no x to the first, so I use a 0 placekeeper, and then minus 36. So this condensed synthetic division, bring down the first term, multiply by 1 is 1, and add to 3 is 4. 1 times 4 is 4, add to 9 is 13. 1 times 13 added to 23 is 36. times 1 is 36, add to 0 is 36, times 1 is 36, and oh, isn't that nice? I got it down to that. So right now, as I'm factoring, I have x minus 1 as a factor, and I have a 1x to the 4th plus 4x cubed plus 13x squared plus 36x plus 36. That's what that's telling me. I'm using those values as my coefficients for that reduced polynomial. So now I want to start with that 1, 4, 13, 36, and 36, which are still factors of 36 over 1, so we still have all the same choices. And this is where I'm going to go ahead and take a peek at the graph to see what I might want to try. You still have to have all the work with the synthetic division, but a peek at the graph can help me narrow it down a little bit. So I just happen to have this graphed in Desmos. And we just saw that at 1, there was a 0. We expect that. It passed through nice and neatly, something that's just a solution once. But what happened at this negative 2 looks like it's a solution, but at negative 2 we have a bounce. Remember, the graph came up and went back down in the same direction. And so that tells me at negative 2, it has to be a repeated root to an even power. Bounces happen when, so if it's a root of negative 2, the factor is x plus 2, it has to be x plus 2 squared or x plus 2 to the 4th. And so, or to the 6th, but that would be too high because it's only a polynomial of degree 5 to begin with. But that bounce tells me something about that root. And so, and it also it happened at negative 2, so I'm going to try negative 2 here, and I'm going to need to put it in there at least twice. And since I'm going to, we'll just go with it like this. So bring down the 1 times negative 2 is negative 2, and 4 is 2. Negative 4 and 13 is 9, and negative 18 and 36 is 18, and negative 36 and 36 is 0, is what we expect. And then I need to try negative 2 again, but I'm going to use the coefficients of the reduced polynomial. And so bring down the first term times negative 2 is negative 2, and 2 is 0. And times negative 2 is 0, plus 9 is 9, and negative 2 times 9 is negative 18, and 18 is 0. And so these were, up here were of x cubed, x squared. So this is going to be x squared. So this is a 1x squared plus 0x plus 9. So that's telling me in my factorized form, I have an x minus 1, then I have an x plus 2, I have an x plus 2 again, and then I have this x squared plus 9. And so we want to include complex zeros. So I know that I have zeros of 1, negative 2 is a repeated solution. But then this right here, x squared plus 9 equals 0. I'm going to get x squared equals a negative 9. And that's going to be x's plus or, excuse me, plus or minus 3i. Because it's square root of a negative, we're going to include complex solutions. So all of my solutions, my zeros, including complex, are going to be 1. Negative 2 is in there twice. And then plus or minus 3i. And so at negative 2, we call that as a root of multiplicity 2 because it's a root twice. And so therefore, I have 5 roots, which I expect because it was of degree 5, if I include multiplicities or repeated solutions, zeros. So there are all of my solutions, and we want all the complex as well. If I needed to whittle something down from degree 5 to something quadratic before I could even solve those for those complex zeros. And I used the graph just to whittle down so that the synthetic division could be a little more focused, but yet you needed to have all of this, and you need to show the factored forms as you're working through those, and how you solve that complex piece, and finally box all your final answers. So that's kind of that process. All right. Complex conjugates. We saw irrational conjugates in the last section, but here are complex conjugates. So pairs of complex number of the form a plus bi and a minus bi, or b is not zero, so the imaginary part exists, it is a complex number, are called complex conjugates. And they said, notice in example 2, 2i and negative 2i. Well, I used a different example, so it was 3i and negative 3i were complex conjugates. And that has to play with this complex conjugate theorem. If f is a polynomial function with real coefficients, and a plus bi is an imaginary zero, then a minus bi is also a zero of f. And so example 3, write a polynomial function of least degree that has rational coefficients, a leading coefficient of 1, and zeros 5 and 1 plus I. And so on this one, my zeros, you should list, are 5, 1 plus I, but because rational are real coefficients, 1 minus I must also be a 0. So you need to use that. So then my factors of this are x minus 5 and x minus the quantity 1 plus I and x minus the quantity 1 minus I. Or in other words, I'm going to have this f of x is equal to x minus 5, x minus 1 minus I, and x minus 1 plus I. And you have to have the detailed work of multiplying these out, or you will not get credit. And the key again is in these two quantities for the complex conjugates, to regroup them like this. So I have this a minus b, should be familiar from the last one, a plus b, so that when they multiply those out, they become a squared minus b squared, which is going to be your x minus 1 squared minus I squared. That's what you want to do. That's what's going to make multiplying this out easier. So I'm going to erase part of that. You can go back and re-listen to that if you need to. Again, very similar to what we did with the irrational conjugates in the last example. So I'm writing this polynomial, so I have f of x equals, I have equal signs as I'm going down, and x minus 5 continues to be brought down. But when I multiply these, it's going to be this x minus 1 squared minus the I squared. So I have x minus 5, and then x minus 1 squared is an x squared minus 2x plus 1. The square of a binomial is a trinomial. And I have minus I squared. And I squared is a negative 1. So that's going to make this plus 1, or I can just put it together and make that plus 2. And then distribute your x. Distribute your minus 5. And then collect like terms. X cubed minus 7x squared plus 12x minus 10. And it's a polynomial of least degree because it has 3 zeros, because if 1 plus I is 1 minus I, because it has rational coefficients, which are real numbers. And so that is of least degree. It has a leading coefficient of 1. And there you have it. You can go back in and check out, does f of 5 come out to 0? Does f of 1 plus I come out to 0? Does f of 1 minus I come out to be 0? It's a little tedious to check the 1 plus I and 1 minus I, but it can be done. All right, so example 4 here, write a polynomial function in factored form. And so save yourself time if those are the directions. You don't have to multiply it out. Of least degree that has rational coefficients and a leading coefficient of 1. So zeros of 2, 2i, and 4 minus root 6. Well, we have to use both the theorem from 4.5b and from this lesson to get all the zeros. Because these have rational coefficients, if 2i is a 0, a minus 2i has to be a 0. And if 4 minus root 6 is a 0, 4 plus root 6 has to be a 0. And so f of x is going to be x minus 2, x minus 2i, x plus 2i, and then x minus the quantity 4 minus root 6, and x minus the quantity 4 plus root 6. And then don't leave the parentheses in there, so f of x is x minus 2, x minus 2i, x plus 2i, and x minus 4 plus root 6, and x minus 4 minus root 6. Excuse me. And so there you have it. That is what I want. And you don't have to multiply it out because it said leave it in factored form.